Okay, so this is our demo for the Floyd-Warshall algorithm. So let's say that this is our graph. Okay, so we're supposed to find the shortest path for all the pairs of vertices. And then this is our sub-problem. So SP of A, B, K just means that you're trying to find the shortest path from A to B using only intermediate nodes 1 up to K. Okay, so we'll be doing this for sub-problems from k is equal to 0 up to n, and in this case n is equal to 5 because we have 5 vertices, so we'll actually be doing this from k from 0 to 5. Okay, so let's start with k is equal to 0. So this is the base case, and if it's k is equal to 0, that just means that we don't have any nodes or intermediate nodes along the path. So what we'll do here is along the diagonal we'll just write zeros. Okay, and the reason for that is because this is from A to A, B to B, C to C, D to D, and E to E, and since you're already at that node, then there is 0 length path. Okay, so that's the shortest path. It's 0, right, since the source is equal to the destination. The next thing that we'll do is we'll just copy all of the edges, edge weights for each edge. Okay, so from AB we have 2, for AE we have 4, for BC we have 3, for CD we have 5, for CE we have 1, for DA we have 8, and for ED we have 7. Now for the rest, that should be infinity. Okay, there should be infinites right there, but to keep the tables clean, I'll just leave it blank, and I'll just leave a note here: blank is equal to infinity. Okay, so just to keep things clean and to make things faster, so that I don't have to write the infinity symbol each time. So this is for k is equal to 0. So again, just write zeros on the diagonal since they're already at the source is equal to the destination, and then you just write all of the edge weights, okay, for each edge. Now let's go to k is equal to 1. So for k is equal to 1, this just means that you can use the nodes from from A to A. So it's just A as the intermediate node, so it's only this one, right? So what we'll do is we'll look at the previous table, so that's k is equal to 0. We'll look at the row for A and the column for A. So we'll put the column for A here and the row for A here. So we'll just copy that. So this is 0 to 4, and then this is 0 here and 8 here. Okay, so what will we do with this one? So I'll show you a shortcut, and what we will do is we'll look at each row and each column. Now if the row or the column is either 0 or infinity, then we will just copy the value. Now why is that? So take note that for the sub-problem SP of ABK, so we're currently looking at k is equal to 1, you'll be either looking at the previous cells in the previous table, so k minus 1. So let's say for example here in AA in k is equal to 1, you'll be looking at AA here in k is equal to 0, so this one. So you'll be looking at the previous cell in the previous table. Okay, so you'll compare that with A k minus 1 plus k b k minus 1, and you take whichever is minimum. So why will we copy if it's infinite or 0 ang row or column? It's because if it's infinity, then that would be either infinity here or infinity here, and infinity plus something will never be chosen for the min value, so we'll just need to copy the previous value. Okay, so if that is infinity. Now if it was 0 naman, Now, if it was 0, what would happen is you'd still have the same value, right? Because you're not adding anything to the previous cell. So, like for example, here in um, let's say in AB, the the row's value is 0, but the column's value is 2. So 0 plus 2, it's still 2, right? So you just copy it right away. So what we'll do is, if it's 0 or infinity, we'll just need to copy. Okay? So let's see what items we need to copy. Okay, so let's change it to red. So this whole row is 0, so we'll just need to copy everything, right? So 0, 0, infinity, infinity, 4, and then this one is also infinity, so we'll also copy everything here. Copy this one, and then same with this row. This is infinity, 5, and then 1. This one is not a 0 or infinity, so we'll leave it as is, but the last row is infinity, so we'll also copy everything here. So infinity, infinity, 7, and 0. Now for the columns, what we will do is, for this one, this is a 0 column, so we'll also copy this one, right? And then this one, it's not a 0 column, so we'll leave it as is. So this one will have a new value, okay, later. This one is an infinity column, so we'll copy that one. Same with here, so we'll also copy this one. But this one is not infinity nor 0, so we'll have a new value here. So what will be the new value? So we'll just compare the current value, which is infinity, and we'll add the row and column value. So this is 8 plus 2, and then this one is 8 plus 4. So we'll just take the minimum, and of course the minimum is the 8 plus 2 here and the 8 plus 4 here. Okay, so now we have our values for the next table. Okay, so that would be 0, 2, 4, 0, 3, 0, 5, 1, 8, and then we have the new value here, 10, right? 0, and then the new value 12, and then 7 and 0, right? So now we have our new values for k is equal to 1. Okay, the next part is for k is equal to 2. So I'll just erase this quickly. So I'll just recycle the tables here, because for now we won't be using k is equal to 0 anymore, right? Because we'll just be looking at the previous value. So we only need the information for k is equal to 1. So we don't even need to look at k is equal to 0's table anymore. Okay, so let me clean this up first. Okay, we're done. So now our goal now is for k is equal to 2. So for k is equal to 2, this means that we can use a or b as intermediate nodes. So what we'll do now is we'll look at the row for b and the column for b, and then copy that just like what we did earlier. So 2, 0, 10, and then for this one it's 0 and 3. Okay, so let's check which rows and columns we need to copy. Okay, so this row we can copy, right, because it's a 0 row. This one also, this is a infinite row, infinite row. Okay, so we can copy everything here. This one, everything in this row can be copied. Okay, same with this row here. This should also be copied. So we won't change anything here. And finally, in the last row, we'll also copy this one. Now for the columns, we'll also copy this one, this one, this one, and this one because they are 0 or infinite columns. So everything here should be copied. Everything here should be copied. Everything here should be copied, and everything here should be copied. So actually, the only thing that would be different would be this one, right? This cell plus this cell, because in this column here, it's only this row and this row that's not 0 or infinity. So we'll only need to check these two cells here for the comparison. Okay, so what we will do is we'll check. So this is the current value is infinity, and then we'll compare that with 2 plus 3. So of course this one will win. We'll get the value 5. Then this one is infinity versus 10 plus 3. So of course this will also win the 13 value. Okay, so we now have our new values for k is equal to 2. Okay, so let's copy all of the values here. So this would be 0, 2. Now we have the new value 5. 4 would be here. 0, 3, 0, 5, 1, 8, 10, and then the new value 13, 0, 12, 7, and 0. Okay, so this is for k is equal to 2. Now next would be for k is equal to 3. So let's just erase this fast. Erase this quickly. Okay. Almost there. Okay. So next is for k is equal to 3. So this is for k from A to C. Okay. So since we're now looking at k is equal to 3, we'll be looking at column C, or row C and column C. So we'll copy that here. So this would be 0, 5, 1 and 5, 3, 0, 13, and then blank. So which rows and columns will we need to check? So we can copy this one, right? We can also copy this one because those are infinite rows and a 0 row. Okay, so let me change this to red. Okay, so we'll copy everything in this row. This one, and then also copy in this column. Okay, and then in this row, for the columns, we'll also need to copy here, here, and here because those are infinity or zeros, right? So we'll copy this, here, everything here. So we'll only need to check actually how many? 6, right? Because those would be this row, and this row, and then these two columns. So that the intersection of those rows and columns would be here, 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 in this 4 cells here. So let's check what would be the value. So we have infinities here, right, versus the value of the row plus the column. So this would be 5 plus 5. So of course the 5 plus 5 will win because that would be the minimum. So that's 10. Here you have 5 plus 1. So this is 6, but the minimum is still 4. So we'll keep 4. Okay. And then here we have 3 plus 5 versus infinity. 8 will win, right? And then here we have 3 plus 1. So we have the 3 here and then the 1 here. So of course 4 will win versus infinity. So you have 3 new values here. Now how about in these two cells? 0 versus 13 plus 5. So 18 is bigger than 0, so 0 will be retained. And then here we have 13 plus 1, which is 14, and 12 is still smaller, so this will win the min. So although we checked 6 cells, we only need to add 3 new values, which is in this cell here, this one here, and this one here. Okay, the other 3 cells we just need to copy their old values. Okay, so we now have the values for k is equal to 3. So let's copy that. 0, 2, 5. We have a new value 10. Still the same value 4. And then next row 0, 3. New value 8. New value 4. And then 0, 5, 1. Copy the rest. 10, 13, 0, 12, 7, and then 0. Okay, so this is now for k is equal to 3. Next, let's look at k is equal to 4. So let's remove everything here in the previous table, so we don't need this anymore. Okay, so for k is equal to 4, this means that we can use the nodes A to D as intermediate nodes this time. Okay, so for k is equal to 4, we look at row D and column D in the previous table. Okay, so we'll copy this row, so that's 8, 10, 13, 0, and 12. And then for the column, it's 10, 8, 5, 0, and 7. Now, there's only few 0 columns here, which is actually only this row and this row. So we'll actually need to check the rest. Okay, because those are non-zero nor infinity. Okay, so we'll just mark the ones that we need to copy. So these are the same values, right? So for this row and then for this column, same values as well. Okay, for the rest, we'll have to check. So for this one, 0 versus 10 plus 8. So for this row, actually, this will all be 10 plus, right? 10 plus, then 10 plus. For this row, this will all be, okay, so I'll write the infinities first. Because we need to compare, right? So for this row, this would all be 8 plus something. 8 plus. This one will be 5 plus something. And then this one would be 7 plus something. Okay? 7 plus. So those that are unmarked that can be copied, we have to compute them, okay, regardless of whether there's already a previous value or not. Because what if a new value could be better than the current minimum, right? So let's now go through the columns. So this column will all have be plus 8s, right? This one will all be plus 10. This one would all be plus 13. And this one would all be plus 12. Okay, so let's now choose which one is the minimum. So 0 versus 18, still 0. 2 versus 20, still 2. 5 versus 23, still 5. 4 versus 22, still 4. So although we computed something in row A, it still stayed the same. Okay, it's still the same values. Now how about for row B? Infinity versus 8 plus 8, which is 16. So we'll have to choose 16. How about 0 versus 18? So still 0. 3 versus 21, still 3. 4 versus 20, still 4. So in this row, we only changed one value, which is this one. Okay, it's a BA. Next row, Infinity versus 8 plus 5, which is 13. So, of course, 13 is smaller. Same with this one, infinity versus 15. So, 15 is smaller. And then 0 versus 18, still 0. 1 versus 17, so still 1. Right? And then for the last row, infinity versus 7 plus 8, which is 15. So, of course, 15 will be smaller. Infinity versus 17. 17 is smaller. Infinity versus 20. 7 plus 13, so it's 20. Okay, and then 0 versus 19, so it's still 0. Okay, so we now have our values for k is equal to 4. So let's write that down in our table. So this would be 0, 2, 5, 10, 4, 0. Then we have the new value here, 16, right? And then 3, 8, 4, and then new value 13, new value 15, same values 0, 5, 1, and then just copy the next row, 13, 0, 12, and then new value 15, new value 17, new value 20, then you have 7, and then you have 0. So we actually have all values now in the table. We don't have any infinities left, but we won't stop here, okay, because this is only for k is equal to 4. We'll still go to k is equal to 5, and this is already the last one. So let me remove everything here in the last table so we can do k is equal to 5. Okay, so this is the last one na lang. And for k is equal to 5, that just means that we can use all vertices now as part of the intermediate nodes in the path. So from A to E. Okay? So this is now for k is equal to 5. Yep. So this is from A to E. So since we're looking at k is equal to 5, we look at row E and column E. So this would be 15, 17, 20, 7, and 0. And then 4, 4, 1, 12, 0. Okay? And we'll notice that the only 0 column are the last rows and last column. So we'll copy this one because this is a 0 row, and then we also copy this one because this is a 0 column. Okay, now for the rest we'll have to compute because they aren't 0 columns or 0 rows. So we'll do the computation again. So this one will have this row will have 4 plus. The next row is also 4 plus. The next row is 1 plus something. And the next row is 12 plus. Okay. Next, let's go through the columns. So this is all 15. This is all 17. This is all 20. And then this is all 7. Okay, so let's try to get the minimum out of each cell. 0 versus 19, still 0. 2 versus 21, 2. 5 versus 24, 5. 10 versus 11, it's 10. 16 versus 19, 16. 0 versus 21 is 0. 3 versus 24, still 3. 8 versus 11, still 8. 13 versus 16, 13. 15 versus 18, still 15. 0 versus 21, of course, it's 0. 5 versus 8, you have 5. 8 versus 27, still got 8. 10 versus, how much is this? 29. still 10. 13 versus 32, still 13. And then 0 versus 19 is still 0. So even though we did a lot of computations, we still got the same values from the previous cell, which means that by going through E, you don't actually improve the current shortest paths. And the reason for that is because, okay, so I'll show you why that is. The reason for this is, if you go through E, what would be the one that changes if you go through E? The path going to D, right? But if you go from A to D, so from A to D, if you go through E, that would cost you 11. But the shortest path is actually not going through E, but going around. So A, B, B, C, C, D. Right? So that's 2 plus 3, 5 plus 5. It's only path of 10. So this one is shorter. So you don't need to go through E. And then the same thing, for example, from C to D. Okay, so from C to D, if you take the path going through E, that would be 1 plus 7, that would be 8. But there is a direct path here, which is only 5, right? So in this particular graph, going through E does not actually improve your shortest paths. But that's not the case for other graphs, okay? It's only the case for this graph. So we still need to do the computations up to k is equal to n. And so it just so happened that everything was the same in this particular graph. So we have 0, 2, 5, 10, 4, 16, 3, 8, 4, 13, 15, 0, 5, 1, 8, 10, 13, 0, 12, 15, 17, 20, 7, 0. Okay, so I'll show you the actual shortest paths for this graph. So maybe I'll show you all the pairs for A and for B. Let's see, so that we can keep this demo a little short because it's already running too long, and you can just confirm for the rest of the other rows. So let's just go through A and B, and then for the others you can check it on your own. Okay, so for A to A, of course it's 0, it's right here. From A to B, it's only 2 because you have this direct path, right? So it only costs 2. From A to C, that would be A to B, B to C. So that's 2 plus 3, you have 5, which is this one. From A to D, you have 10 because it's the same path. A, B, B, C, that's 5. And then plus 5 here, you have 10, right? So you have 10 here. And then from A to E, you just take the direct edge, which is this one, which is 4. Okay? Now, how about for B? Okay, so for B, I'll change the color. So I'll change this to red. So from B to A, it costs 16. Why is that? Because we need to go around. Okay, where will we go around? Here, B to C, 3. C to D, plus 5. So that's 8 already. Then from D to A, that's plus 8. So 8 plus 8, that makes it 16. Okay, that's from B to A. From B to B, of course, it's 0. And then from B to C, it's 3 because you can take this direct edge, right? From B to D, it's 8 because you have B to C and then C to D. So that's 3 plus 5. And then from B to E, it's only 4 because you take BC, which is 3, and then CE, which is 1, so that makes it 4. Okay, so you can confirm the rest of the rows for C, D, and E and check that it is indeed the shortest paths. Okay, so that is our demo for Floyd-Warshall algorithm. Okay, so this is our demo for Johnson's algorithm. And so we're given this graph, and we'll notice that there are negative edge weights, right? So for Johnson's algorithm, to solve the all pair shortest path, what we'll need to do is add a new vertex. We'll call it S for now. So let's add a new vertex S here. And then we will connect this vertex S to the rest of the edges, or the rest of the nodes. So we'll connect S to A, S to B, S to C, S to D, and S to E. And those will all have 0 edge weights. So this would be 0, 0, 0, 0, 0. So this is our new vertex, and then we added edges from S going to the other vertices, but there is no edge going into S, only going outwards. Okay, and they all have edge weights of 0. So the first thing that we'll do for Johnson's is we will run Bellman-Ford. Okay, so we'll run Bellman-Ford algorithm on this graph, because Bellman-Ford is the safe algorithm to use, because we have negative edge weights, and we don't know for sure in general whether there are negative edge weights or not. So we'll just use Bellman-Ford so that it's general. Okay, so this is the same graph earlier. Okay, it's the same one, but this time the nodes going from S doesn't have any edge weights, just to keep it clean. So just imagine that the edge weights for S going to A, S to B, S to C, and so on are all 0. Okay, so let's run Bellman-Ford algorithm on this graph. So we have set the order of the edges here, and we will just go through each one and try to relax them. So let's see. AB, relax, no. AC, no. AE, no. BD, no. BE, no. CB, no. And for a lot of this in the first round, there won't be any relaxation, since their starting scores, or starting shortest path value, is currently infinity. The only ones that could improve are actually those that start with S, because they are 0. The current shortest path length is S. Okay, so since we're running this shortest path, or single source shortest path starting from S, then it will have the value of 0 at first, right? So we are now at the point when we're going through the edges starting from S. So SA, can we relax this one? Yes, we can. So that's 0 plus 0. It's 0, which is better than infinity. So yes, so it becomes 0. A becomes 0, previous of S. And then SB, can we improve this one? Yes, so that's 0 plus 0 again. C, also 0. D, also 0. E, also 0. So we have now improved all of them. So let's now go to the second iteration. AB, can we improve this one now? 0 plus 3, is that better than 0? No. AC, no. How about AE? So this is 0, and then you have minus 4. Is that better than 0? Well, it will be, because that's negative 4, right? So we will actually relax this one. So E becomes negative 4 this time, and previous is A. Okay. How about BD? 0 plus 1? No. How about BE? Is 7 better than negative 4? No. CB? No. DA? No. How about DC? This one will actually relax, because that's 0 minus 5, so that's negative 5, and that is better than 0, because negative 5 is smaller. So we will relax this one. So C becomes negative 5 with the previous of D. Okay, so we change it here. ED, will we improve this one? So that's negative 4 plus 6, so that's 2, but that is not better than 0, right? So still won't relax this one. SA, still the same. SB, the same. 0, 0, is it better than the current one, which is negative 5? It's not. SD, no. SE, no, right? So since we have 2 relaxations, we'll continue with the next iteration, which is now iteration number 3. So we'll start again at AB. Won't relax this one. AC. How about this one? 0 plus 8, so that's 8. Is that better than negative 5? Well, it's not, so no. AE. AE is 0, negative 4. It's still the same, right? So, won't relax this one. BD, no. BE, 7 better than negative 4? No. How about this one? Negative 5 plus 4. This would be negative 1, right? So that is better than 0. So we will actually relax CB. So B becomes negative 1 previous of C. DA, no. DC, still the same. ED, no. SA, no. SB, no. SC, no. SD, no. SE, no. But since we have one edge that we relaxed in this round, so we'll continue with iteration number 4, right? So this is actually the last iteration anyway, or it's actually not, because we have 6 nodes here. So A, B, C, D, E, and then S. So our maximum is up to 5 iterations. So we're still in iteration number 4. So let's see. AB, no. AC, no. AE, no. BD, no. BE, no. CB, no. DA, no. DC, no. ED, no. SA, no. SB, no. 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 So since we did not relax any edge in this round, then we can stop early. Okay? So this is already our shortest paths. So from S to A, it's 0. From S to B, it's negative 1. And that is if we take the path from... Okay, so let me draw this one. So the path from S to B with negative 1 is if you take S to D. So that's... S to D is 0. D to C is negative 5. And then C to B is 4. So that's negative 5 plus 4. So you have negative 1. Okay. S to D is just 0 here, straight up. And then S to E is also negative 4. That's because you can take S to A, which is 0, and then minus 4. So you have S to E. Okay. So those are your shortest paths. So remember, A is 0, B is negative 1, C is negative 5, D is 0, E is negative 4. So let's write that down here as their scores. So A is 0, B is negative 1, C is negative 5, D is 0, and E was negative 4, right? So let's double check if we got it right. So 0, negative 1, negative 5, 0, negative 4. That was here, right? 0, negative 1, negative 5, 0, negative 4. So we got that right. And so our next step here is to actually reweight the graph. So given these scores that we got from the Bellman-Ford, so we will fill in the values. So remember that in reweighting the graph, we would have SP of AB is equal to the current weight SP of AB, and then plus the score of the first endpoint A minus the score of the second endpoint B. Okay, so we now have our original edge weights here, 3, 8, negative 4, and so on. So we will write the plus scores of the, what do you call this, the first endpoint. So for all A's, that would be plus 0, 0 here. For B, that would be negative 1. So minus negative 1, plus negative 1, negative 1. Are there any other B's? There's also one here. And then for C, that would be negative 5. There's a negative 5 here. Minus 5. negative 5. And then for D, it's 0, right? And then for E, it's negative 4. Okay, so negative 4, negative 4. And then we will compute it for each one. So for AB, that would be 3 plus 0 minus negative 1. So this is actually plus 1, right? So AB will become 3 plus 1, which is 4. So we'll write that here. This one is already 4. For AC, that would be 8 plus 0 minus negative 5. So this is actually plus 5, right? So 8 plus 5 is 13. So AC would be 13. It's here. Okay. AE naman, they have negative 4 plus 0 minus negative 4. So this is actually plus 4, right? So negative 4 plus 4, AE would be 0. Okay. BD, we have 1 minus 1 minus 0. So BD would be 0 because you have 1 minus 1 here. Okay, so BD is 0. And then BE, you have 7 minus 1 minus negative 4. So this is plus 4. So 7 minus 1 is 6. And then plus 4, you have 10. Right? BE. So BE is actually 10. Okay. For CB, B, sorry, not B, but 4 minus 5. So that's negative 1 minus negative 1. So this is plus 1. So negative 1 plus 1, CB is 0. So that's 0 here. And then DA, you have 2 plus 0 minus 0. So DA is 2. So this still remains 2. For DC, you have negative 5 plus 0 minus negative 5. So this is plus 5, right? So negative 5 plus 5 is 0. So they cancel each other out, right? And then lastly, for ED, so that's 6 minus 4. So this will become 2. So that is for ED. So this is now our reweighted graph, and you'll notice that all of the edges are now non-negative, right? Because we used the scores that we got from Bellman-Ford, and then we applied this equation for the reweighting of the edges, and then now all of our edges are already non-negative. And because they're non-negative, then we can run Dijkstra's algorithm n times, one for each node as the source vertex. Okay, so let's use this reweighted graph here and run Dijkstra's n times. Okay, so let's see that here. So I've placed the reweighted graph here, right? So 4, 13, 0, 10, 2, 2, 0, 0, 0. Let's check if that's the same. So 4, 13, 0, 10, 2, 2, and then triple zeros here. So this is the same. So let's run Dijkstra's starting at A. Okay, and if you remember Dijkstra's, this will choose between these three candidate edges, and the minimum here is of course AE. So we will relax AE because 0 is better than infinity. So E will become 0 with previous of A. Then after that, the candidate edges would be this 3. But the minimum would be ED because it only has 2, right? So ED will be relaxed and D will become 2 previous of E. After that, minimum is DC, right, with 2 as well. So this will be relaxed to 2 with DC or C being 2 and then previous of D. After this, there's only 2 candidate edges and the minimum is CB with 2. So B will become 2 and previous of C. So this is now our shortest paths starting from A to other vertices. So let's remember it's 0, 2, 2, 2, 0. So let's write that down here. Okay. So you have 0, 2, 2, 2, 0. Okay. That was when we started at A. Now let's redo this. But this time, let's start at Okay, let's start at B. Okay, so if we start at B, okay, so the candidate edges first would be BD and BE, and of course the minimum would be this one because it's 0. So we will relax this one, D will become 0. Okay, and next candidate edges we have 3, and the minimum is DC also with 0. So we'll relax that one. And then next candidate edges we have only 2 now, and the minimum is DA, so we'll relax DA, A becomes 2. And then finally for this one there's 2 candidate edges, the minimum is AE, so we'll relax AE and E becomes 2. So now our shortest paths starting from B would be 2 0 0 0 2 as well. So let's write that here. 2 0 0 0 2. Okay, now let's do that again, but this time starting at vertex C. Okay, vertex C, let's see. Okay, so from C there's only one candidate edge, so of course we'll relax this one, CB, B becomes 0. After that you have 2, you choose BD with 0, and then next you have 2 again, so this time it's DA with 2. Okay, and then after that same thing, you have E with 2. Okay, so it's also the same, 2 0 0 0 2. Let's write that here, 2 0 0 0 2. And then after that let's run it starting at D this time. Starting at D, we will have 2 candidate edges, but then the minimum is DC with 0, so we'll relax C. And then after that there are also 2 candidate edges, but this time the minimum is CB with 0. After that DA with 2, then AE with 2, and that's it. So it's also 2 0 0 0 2. Okay, so let's write that down here, 2 0 0 0 2. And then finally we'll run it starting at vertex E as the source point. So at E there's only one candidate edge this time, and it's ED, so we'll relax this one, D becomes 2. After that you have C or D, DC as the minimum, so you have C becoming 2. After that you have CB winning with 2, so we'll relax that one. And then finally you have DA with 4, right? So A is actually 4. Okay, so this time it's 4 2 2 2 0 starting at E. Okay, so that's 4 2 2 2 0. Now this is our value for the n-Dijk stress, but this is for the reweighted graph. We want the all pair shortest path for the original graph. So what we'll do is we'll need to readjust the shortest path lengths using this equation. And earlier when we added CA and then subtracted CB, so to counter that we will subtract CA and add CB back. Okay, so it's just the opposite. So plus CA, here it's minus CA, here it's minus CB, here it's plus CB. Okay, so what you'll need to do is so for this one, so since this is the starting, or this is this source vertex here, we'll write the negative. Okay, so that's here, negatives of CA. We'll write the negative score in this one. So this is minus 0, minus negative 1, so this is actually plus 1, minus negative 5, so this is actually plus 5, and then minus 0, and then minus negative 4, so this is actually plus 4. Okay, so let's write that for all rows. So minus 0 for all of this cells in this row, and then this is plus 1, and then this is plus 5, this is minus 0, and this is plus 4. Okay, and then finally we'll also do that for the columns. So for the columns, I'll change the color. Since this is just plus CB, so you'll just write the scores as is. So this would be plus 0, plus negative 1, so that's minus 1 actually, plus negative 5, so this is negative 5, plus 0, and then plus negative 4, so this is minus 4. Okay, so let's write that down for each column. So this is all plus 0, this is minus 1, this is minus 5, this is plus 0, and this is minus 4. Okay, so we can now compute everything, the readjusted lengths. So let me bring this back to blue. So this one, if you compute all of these values, I'll just write it down so it's faster. So this would be 0, 1, you have here negative 3, 2, negative 4, 3, 0, negative 4, 1. This one is 3 minus 4, so that's negative 1. And then you have 7, 4, 0, 5, 3. This is because it's 7 minus 4, so that's 3. And then you have 2, minus 1, minus 5, 0, negative 2, 8, 5, 1, 6, and then 0. Okay, so just double check if the computations are right, but it's supposed to be correct, right? 0, 3, 7, 2, 8, 1, 0, 4, negative 1, 5, negative 3, negative 4, 0, negative 5, 1, 2, 1, 5, 0, 6, negative 4, negative 1, 3, negative 2, 0. Yeah, so this is the final, what do you call this? Final all pairs shortest paths. So I'll show you some of the paths here. So I'll do this for 2 rows again, so for A and B, and then I'll just leave it to you to confirm that it's also correct for the other 3 rows. So let me do it for A. For A, so A to A is of course just here, so A to A is length 0. A to B is 1 because okay, so how will we pass through A to B that only has cost of 1? So we could actually go around. So instead of going directly from A to B, which is 3, using this edge, we'll actually go around. So negative 4 plus 6, so that's 2, minus 5 is negative 3, right? Plus 4, oh sorry, so negative 4 minus 6 is negative, so 2, and then minus 5 is negative 3, and then negative 3 plus 4 is 1. So you have the 1 here. Yeah. Okay, sorry for the confusion. And then from A to C, so still the same path. So negative 4 plus 6, so that's 2, minus 5 here, so that's negative 3. And then A to D is just the same thing here. So negative 4 plus 6, so that's 2. And then from A to E, is negative 4. Okay? And then for B, okay, let me change the color. I'll actually just erase everything so that it's not too cluttered. Okay, so let's clean it up first. And then for B, B to A is 3. So how did we get 3? We can actually pass through here, 7. Or sorry, it's not that one. So how will we get to A with only 3? It's actually this one, right? B to D with 1, and then D to A with 2. So that's 3 in total. Then B to B is only 0 because it's already there. B to C is negative 4. Okay, so how do we get negative 4? So from B to C, we pass through D, so that's 1 minus 5. So that's negative 4. Okay. And then from B to D is of course direct 1, which is just 1. Then from B to E, it will take negative 1. Okay, how will we get there? From B to E. Okay, so erase this. So we'll actually pass by the same path going to A, right? So we'll take B to D, 1 plus 2, 3 minus 4, negative 1. So you have the negative 1 from B to E. Okay, so I'll just leave it to you to confirm the 3 other rows, whether they are correct for the all pair shortest path on this original graph. So these are the correct values already. Okay, so that's the demo for Johnson's algorithm.